I am so glad you convinced me that the family car should be the Defender 110. It is so beautiful inside. It's so comfortable, and it just feels indestructible.
Yes, it really is. I've been waiting a long time for the new model to come out. The Defender 110, I'm telling you, it's my favorite car of all times. It's my third one. You know, I have stories of going off-road. The guy managed the group. He was like, what are you doing in this beautiful car? I'm like, I'm going off-road. He's like, are you sure? Because you can use one of ours. And then they look like Mad Max cars. I'm like, no, we're going to do this. And he was shocked.
Wow. Well, it's great because the Defender has been reimagined for 21st century adventure, and its unparalleled off-road ability, as well as its robust interior, are invaluable whether you're headed towards uncharted territory or just a weekend of exploration. The Defender 110 tackles challenging surroundings with absolute confidence. The SUV conveys strength outside and in, featuring peerless technology like an intuitive driver display and an award-winning infotainment system. That's my favorite part, to keep you connected no matter where the journey takes you. Adventure is unique to everyone, and so is the Defender. Choose from the two-door Defender 90, the four-door Defender 110, or the larger Defender 130 with the ability to seat up to 8 passengers. You'll find uncompromising performance in all three. So pack up and go even further with the Defender 110. Learn more at LandRoverUSA.com/Defender.
These days, we're all investors, trying to be smart with our money despite our worst impulses. But at iShares, we believe that deep down inside of every investor is a better investor. One that's just waiting to be let out. Explore iShares ETFs and insights and let your best investor out. Visit iShares.com for more information.
This isn't your average business podcast, and he's not your average host. This is the James Altucher Show.
James, there's another one that's like Steven Pinker, you know, the famous Harvard psychologist. There's this effect that you can get people to change their minds. So you say, like, you go out to dinner, waiter says, we've got blueberry pie and we've got apple pie for dessert. Which would you like? And then you say blueberry. And then they go into the kitchen and they come back out and then they say, oh, we also have rhubarb pie. And then and they say, oh, in that case, I'll have the apple pie. Like, you just gave totally useless, like the original choice was blueberry versus apple. Then you got irrelevant information. Like, it could be like the Padres won. Oh, okay. Then I'll change my order from blueberry to apple. But it's like the additional information causes this bias to the human mind that now they're going to invert. It's like the prisoner's dilemma or something. Like, you have to change your frame immediately.
Well, you know, there's a math problem that parallels that, right?
The Monty Hall problem.
Yeah. So I wonder if it's in the brain somehow connected that way.
Yeah, that's interesting. Yeah, I mean, just in terms of like, there's no actual information that I can, like, literally I could say there's an old Ford Model T down the street, and there's also now I changed my order, please.
You know, there's 2 persuasion techniques, just real quickly, that I really think are useful. One is shaping, which is, let's say you're talking to a boss and you want a raise. You know, you say something like, oh, is that, a photo of you with your kids? Oh, you're such a generous father. You know, that's really great. So now you've shaped them into, now they don't want to disappoint you that they're not generous. So then you could switch topics and put them in a position where they're forced to be generous, and it's harder for them to say no. So that's called shaping. Right. And then this is one I use in negotiation. Like, this one has made me money. It's, let's say you're negotiating, like for me, the sale of a company, and the person says, and we all agree we're going to sell the company. Now the buyer says, okay, well, how much do you want? And there is an anchoring bias you can use, like, oh, I was thinking of $1 trillion, and then you all laugh and whatever. But after that, I always say, listen, I've been hard at work building my business. We've been talking about all these synergies and what we could do. This could be a massive company with the combination. But you're like the grandmaster at doing deals, and I'm just like an amateur. Like, I know this. Can you give me
advice? Right.
And I say, can you, if you were me.
What would you tell me? Right, yeah, exactly.
Just being like friend to friend here for 1 second. Mm-hmm. If you were me, what would you ask? And now I've given them status, and they don't want to ruin. That's a big deal. I gave them dopamine. I gave them like a literal dopamine injection. They don't want to ruin that. And so they're going to give me good advice.
Right. I'm the type of guy that he respects, and he's the type of person who is wise enough to Yeah, that guy Chris Voss. I think you had him on your show.
Yeah,
that never split the difference. Yeah, one of the persuasion elements is ask them what they would do in your situation. Like, oh, I've only got 30 grand. I want this Toyota Tacoma. It's 38 grand. I'm sorry. I gotta. What would you do? If you're me, I got $30,000 in my pocket right now. But. And then it's like 10 hours later, going back to the manager, and gets the car for $30,000. Yeah.
Well, I think the actual thing there he says is, let's say the terrorists say, I need $10 million in cash in an hour, and at this airport, and Chris Voss will say, great, just tell me how I can do that physically, and that always, puts them into, can't physically do it. So they have to figure it out. And you've told them yes. And the only thing they have to do is figure out a solution to get
and
it done.
You've recruited them now they're on your side, even though they're kidnapped your kid, right?
Right. So one interesting outcome of all this stuff is that the silver lining is it's given me extra exercise that you don't normally get for building a thicker skin.
Yeah.
Because I've already had now 2 ex-girlfriends write articles about me.
Great.
And a close relative write an article
about me. Are you serious?
Yeah.
Look, let's just not BS about it. You're extremely intelligent. You're very successful. They're just jealous and envious, which are the worst traits, corresponding opposite traits of gratitude or jealousy, envy. You're very interesting because you're not religious, and and I'm not saying, religion is like a panacea, Judaism's about, but there's so much depth that there's so many interesting things about Judaism that I would love to talk to you about someday. Because it sounds like it's totally irrelevant. I know Solomon was going to split the baby, but there's actually a tremendous amount of practical wisdom, or just here's one piece of wisdom that you may or may not know. In Judaism, it's considered a sin to go into a store when you're not going to buy that new Shure HMB microphone, Jay, and you're going to buy it on Amazon, but you want to check it out. You're not allowed to do that and go into the store when you know for sure you're not going to buy it. If you have a doubt, you might buy it, you might not, that's totally kosher. But you're not allowed when you know for sure, I'm going to buy it on Amazon, but I want to make sure I really like it before I put down the $800 to Jeff Bezos. Then they take that law and they make all sorts of very interesting extrapolations. It's unlawful and it's immoral to go out with a girl just to have, sex, physical pleasure, when you know for sure you're engaged, you're married, you're going to marry somebody else. These girls are just for fun and I'm going to marry. That's considered a sin. That's derived from the same legal principle of going into a store. It's called stealing thoughts. When you come into my store, you're raising my hopes. And it's kind of like we're transacting a little bit. Every person that comes in, there's a probability they're going to buy. And especially when you steal the time of the sales clerk or whatever, it's considered pretty bad, actually, because you're doing something against the better interest of the other person, and they don't have symmetric information. But I'm just telling you this is from 2,000 years ago.
Yeah, that's really great.
And there's so much, I would love to do a Talmud class with just take the juiciest bits of the Talmud, the splitting the baby. They're very famous things, like the one I just told you about. There's things you happen to be in Australia and your friend's daughter's getting married, and you're and he sees, he's like, oh my God, you're the only one who came to this wedding from us, and you're like, I just came here for vacation. It happened to, oh, you're such a good friend. And this has actually happened to me. Things like that have happened to me. And again, it's the sensitivity level, but then coupled to the legal principles. I mean, a lot of it's stuff that's not relevant about which kind of animals we shouldn't talk about that, but I think it'll be really unique and fun for you and I. Yeah. I'm not I'm not wearing a yarmulke, whatever.
No, but I have a lot of respect for all that. And particularly with Judaism, there's so much encoded in the language that's very...
It's very encrypted. Yep, that's right.
Yeah.
Yeah. I'll just give you one quick thing and we should get started. The word for hand in Hebrew is yad, which has 2 letters, yud, which is the little dot thing, and then dalid, which is a door. Anyway, every letter in Judaism is a number. So their numerical system is A is aleph, aleph bet. So aleph is 1, bet is 2. And if you look at what the value of dalid, which is D, so that's 4. So you add 4 to the number 10, which is yud, that number is 14. And then you look at your hand, how many bones does your hand have in it? Well, then your fingers. Yeah. It's got 12 plus 2. So
who thought of that?
You never thought about it. Yeah, I mean, but there's so many things like lave, like means heart, and it corresponds to certain, like even though the one like high, like 18 is a lucky number in Judaism. That's because the numerical value of het and yud, 10 plus 8. So, and they have these really interesting connections, like wine. The word for wine is like 2 yuds in the air, so they're like kind of like spaced out, floating around in the air. Anyway, we could get, that's called gematria, which means like geometry, but it's really mathematics. But getting into some fun, like here's a law from like 2,000 years ago about an ox that you knew had gotten out of your farm and it ate somebody else's grass. And we can directly translate that into like tort law of an insurance company and why they deny a claim on a car. Like it's perfectly aligned with our modern legal laws, but nobody ever knows that because no one really thinks it's relevant. Oh, who cares about some stupid ox from like 2,000 years ago? No,
it's interesting because people often trace back, laws like the Constitution to the Magna Carta or even to the Code of Hammurabi, but it probably is actually more likely to have come from these Semitic cultures.
Exactly. Yeah. And in both, right. So let's do that after we finish our.
But I just want to make one analogy to the store. Like you go into the store knowing you're not going to buy. I don't know how to finish the analogy. I'm just going to start it.
Yeah.
Which is, it's like Hawking radiation. Okay.
Yes.
The idea that, something which nothing can escape from it, but except a tiny piece of information.
Yes.
And so, somehow or other, that's conveying, the information that just the fact that we know the black hole exists, there's Hawking radiation coming out of it.
Yeah.
And
the holographic principle, right? The external encodes properties of the internal. That's right.
But I'm trying to figure out how to finish the analogy. I have to show that that's bad or distorted somehow.
I thought you were going to go like, that's why we have a 2-drink minimum at the comedy club. Like, stand
that would be great. But like, what would be like in your situation? It's bad to get information, but not any mess.
Yeah,
and
it's right. It's like
so what's bad about getting the information in this black hole situation?
So I wouldn't do it just specifically in a black hole. I would translate it to like quantum mechanical measurement and observation, the famous Schrodinger's cat. So when you do the observation, before you do the observation, the cat is fat, dumb, and happy, but you could actually kill the cat by observing it, right? Because you have to interact. One quantum system, a photon, interacts with a quantum superposition system of the cat. And so the cat would rather not look at it, quite frankly, because the actual observation in the Copenhagen interpretation collapses the wave function, and people like Hawking, et cetera, ascribed, and that's one of the topics we have today, is this notion that there might not be a unique wave function of the whole universe. And if that's true, or the wave function might have certain properties, like it doesn't depend on time at extremely early times, and then something magic sort of happens in a quantum process that causes it to acquire a time-like property. And those are some of the things that are very interesting. But the act of observing something, so when the shopkeeper observes you coming in, your photons are making him happy, and you're unrealistically raising the expectation value of his wave function and his spirit, and then you're actually concealing the fact that you're this phantom, like you're not going to buy, you're definitely not going to buy. And in that case, I think it could be, we could maybe tie it to the quantum measurement problem. But yeah, the black holes, not so much, except for the fact that black holes swallow up all information. That's the problem, right?
All right, so we'll start. And so we kind of really only got...
We just ended up with the Big Bang itself, like the classical notion of the Big Bang. We talked about the eternal universe, the steady state universe.
Yeah, we talked about steady state, quasi-steady state, Big Bang.
Two of the foremost proponents of alternative models to the Big Bang, Sir Roger Penrose of Oxford and Sir Paul Steinhardt. Now he's not Sir Paul, but he's the Einstein professor at Princeton University.
And I've read about him. His view is essentially almost like magical thinking, that we would think that there's a Big Bang.
Well, yeah, and worse than that, or better than that in some sense. So he was one of the fathers of the inflationary theory. Actually, the model that actually worked, it was the original model was proposed by a guy named Alan Guth at MIT, but then it had so many problems to it that several different people, including Guth himself and Hawking and my friend Paul Steinhardt, had to really implement these radical changes to it in order to get the universe to actually exist. Because as I'll talk about when we talk more about inflation, it's very hard to turn off the switch that causes the universe to expand and inflate. Like it's easy. It's not even easy to get inflation started in the first place. You need quantum tunneling. You need to have a pre-existing multiverse. All sorts of interesting things have to exist there.
Well, maybe.
Maybe. That's right. Yeah. But in Paul's model, he does away with inflation, even though he created it. So it's kind of like, if Steve Jobs came back after he was fired from Apple, and then he came back, and then the first thing he did is destroy Apple, it would have been a very different timeline. But he's one of the fathers of the modern interpretation of how inflation works, and he disavows paternity. I always joke with him, you're like trying to be a deadbeat dad over here. I mean, you started this whole idea.
So actually then to recap from the last time, just a very quick timeline. There's this Big Bang that's mysterious, and there's lots of sources of the Big Bang, which we'll discuss. And then there's this very extremely fast, like not even that, like 1 to the negative 30th seconds period where the universe expands unbelievably quickly. That's this inflationary period. And then it starts to cool down enough where you have subatomic particles, and then much later, hydrogen, helium, plasma, and that's the cosmic background radiation, and then that's the universe we know of after that.
Except for one thing, in that some models, you don't need the Big Bang to be time equals 0. So I was under the impression that's what you wanted me here on the show about. So if that's not, I'm going to say no comment. I'm going to deny the allegations and the alligator. No, the Big Bang doesn't necessarily have to be time equals 0. It doesn't have to be the creation of the universe. In fact, there might not be a single creation of the universe. So even within what we just talked about, the inflationary paradigm, which is not even a theory in a sense, that it's not even predicated upon axioms that themselves are well-founded. Here's the way I prefer to look at it, and I thank a gentleman by the name of Sean Carroll, who's at Caltech, very famous author and physicist. He says the best way to think about the Big Bang is by going backwards in time from today. Now, the problem is it's kind of like Zeno's paradox. You don't know when you're going to stop when you go backwards. If there is no beginning of time, right? Let's say there is no beginning of time. Where do you define, where you're going to stop being able to go backwards in time? So right now we know what it means to go backwards in time, even though we can't do it. I think we'd both do things differently if we could go backwards in time. We don't know how to go forwards in time except by letting the arrow of time take us into the future. But even if we could go backwards in time, eventually we'd come to a point where the laws of physics are unknown to us, and that we have no mechanism to establish how they actually began to exist in the first place.
So just to ask about that, I'll always try to bring it to the layman. Mm-hmm. So the laws of physics and even the laws of quantum mechanics, they are laws that apply to very specific things like light, energy, mass, atoms, and quantum mechanics are laws that apply to quarks, other subatomic particles, and so on. But when people discuss the Big Bang, they're discussing some singularity which is infinitely small, and we just don't understand what that means. There's no concept, as you pointed out last time, there's no real concept of, we don't know what infinity looks like.
Yeah, we don't know how to deal with it. But even what you're saying now isn't completely, so I want to be completely accurate. I'll never dumb it down. I mean, we'll translate it so other people can understand who are experts. I hate the phrase dumb it down. It's so insulting. Even when people say, oh, can you dumb that down for me? I'm like, no, I'm going to respect you. I'm going to treat you like an equal who's just not an expert in my particular field. But if I can't explain it to you, I'm pretty much a loser as a physicist. So my goal is to make it as simple as possible, but not simpler, as Einstein said. So let me just say the following. It may not be necessary to go to a singularity, which is this incomprehensible thing that you just aptly described. It may not be necessary to get to that point, literal point of zero dimensionality. That might be a good thing, and some people are motivated by that very fact. How does something that's three-dimensional, like our normal world, up, down, left, right, backwards, and forwards, how could that emerge from something that has zero dimension? We think of everything, even a flat, like, have you ever seen a triangle?
Like an actual triangle?
Yeah.
Have
you ever seen a triangle?
Well, I guess in the sense that any perfect geometric shape I've never seen.
Yeah.
But yeah, I've seen things that are triangles, but yes, not
properties, right? But it's drawn on a piece of paper, so it's actually three-dimensional, not two-dimensional. The points at the vertices of those are not zero-dimensional points. They're actually three-dimensional dots of ink or pixels on a screen, or even stars in the night sky. They have actual tremendous sizes. So there's no such thing, except in the abstract world of the mind, And yet, scientists who would purport that there is a singularity really do mean essentially an infinitesimal amount of space in an infinitesimal amount of time. But that's a long-winded way of answering this question, that the way we should think about it is counting back. What was yesterday like? What was a year ago like? What was a billion years ago like? What was 13.8 billion years ago like? And we actually have very good answers to all those questions. We actually know what it was like 380,000 years after the Big Bang. That's when the cosmic microwave background radiation that I study with BICEP2 and with the Simons Observatory, that's when that was created. That was when it was produced, because it was produced from the formation of hydrogen out of bare protons and bare electrons coming together, coupling together, and forming atomic hydrogen, which is a state of hydrogen with equal number of charges, positive and negative. And then if you go from that date, whatever day that was, that has a day. In other words, if we count back 24-hour periods, James, we can go back to that moment. Okay, it wasn't actually a moment. It actually took tens of thousands of years. But let's say the very first hydrogen atom in the universe, that exists, right, as a concept. You can conceive of somewhere at some moment in time, the very first stable hydrogen atom formed. Right? You can conceive of that, James?
And just to understand, is that because let's say the second before then, there was still all these subatomic particles and neutrons, electrons, protons floating around, but things cooled enough that the strong nuclear force kind of melded them together into an atom?
Not the strong nuclear force, but actually for that we have to go way back in time, and we'll get there. But for now, it was a chemical ionization of hydrogen into individual proton and electron plasmas. So before that moment, whatever day that occurred, literally on a calendar, we could construct it in principle, but we could go back in time. There's a day when the very first hydrogen atom was able to join together a proton and an electron and make a stable atom that never got broken apart by a blast from a hot photon that was existing earlier in time. That doesn't mean that all the hydrogen in the universe formed at that time, but over about tens of thousands of years, the hydrogen did form. And that happened on a day. Let's call that Tuesday, 380,000 years.
And that's before the plasma, which is what we see when we turn on or when we used to see when we turn on the TV set between channels, that static.
Yes.
That's the kind.
Yeah.
And your goal again with BICEP2, the telescope, was to see past that, but you couldn't see light. You had to detect gravitational waves. So how do we know there was a time before that, actually?
Yeah. So in order to have that exist, you have to posit that the laws of chemistry were the same prior to that epoch as they are, today. Essentially, that hydrogen cannot be present when there's a certain amount of energy that we term in terms of electron volts of energy. And if you remember from chemistry class in high school, perhaps you'll remember this 13.6 electron volts. So if you take a plasma globe that has hydrogen gas within it, and you shock it with 13 volts per electron that's in there. So it could be a tremendous amount of current required to actually dissociate the electron from the proton. They will break apart. They did the same today. They did it yesterday. They did it 100 years ago. They did it thousands of years ago. It happens in the galaxy, in our solar system. We can watch it occurring today at high redshift, at long times ago. So we know the laws of chemistry haven't changed. The laws of nuclear physics haven't changed in billions of years. And so we just asked the question, if there were two separate gases of protons, one of protons and one of electrons, suffusing all of space and all of time at an early point in the universe's history when it was much denser, on average more hot, more compact, that universe would not be able to sustain atomic hydrogen, which is a proton bound to an electron. Instead, times before that, all the protons and electrons would be separate, and times after that, they would all be in the form of hydrogen. That's a pretty good approximation to the state of the universe if you go back 13.8 billion years ago. Now, the question is, we don't want to go only back to when that first hydrogen atom formed. Now we want to ask the question, how did that proton form? That's a different question. The proton that makes up the hydrogen atom's nucleus, the hydrogen's simplest atom on the periodic table, has just one proton, one electron. How did the proton form? That is a very, very complicated question, but that takes us into the realm of the nucleus. So the nucleus is made up of two quarks and an antiquark in the case of a proton, and those quarks and antiquarks have to bind together the same way that the hydrogen atom bound together to make a stable atom of hydrogen, of atomic hydrogen. In the case of the proton, at times earlier than about 380,000 years. Now you go 380,000 years and you go backwards in time 379,999.9999 years and 1 second less than 380,000 years. That's when that proton could form. That's when the quarks were not getting jostled by the constant impact of the heat of the photons to break them apart. And that's called, this coupling process that causes the protons to form. It's hadronization when these heavy particles called protons formed.
How do we know there was a second before that first hydrogen? Because you can't see past the cosmic background radiation. How do we really know anything about the
How do you know who your
that?
father is? Your mother told you who it is.
Exactly, but no one told us about. God doesn't tell us about this.
Right. Yeah. So always we have to make a naturalistic assumptions. We have to assume that there are certain immutable laws of nature, or laws can change theoretically, but we understand the properties today, and we have some way of reconciling what they would have looked like retroactively in the past.
So we're pretty, even though we can't observe it. Or,
we can observe. No, we can observe. We can form a proton. We can actually smash protons apart and they make other quarks, and then those quarks recombine so quickly to make protons and other heavy particles. So we can actually test exactly what you just said on Earth, and then we make the simple, relatively straightforward, metaphysically at least, statement that the laws of physics haven't changed in 13.8 billion years. And you would have to tell me a reason why I shouldn't believe that the laws of physics haven't changed. In other words, has the speed of light changed? Has the nuclear binding force changed? Has the electronic hydrogen ionization energy changed? We have no evidence for it. So you telling me that you don't believe that, actually the burden's on you to come up with a mechanism to explain how things could have been otherwise. But we didn't see the moon form either, but we understand the process of planetary aggregation, we didn't see the supernova that exploded 5 billion years ago in our solar system neighborhood of the galaxy. We didn't see that either, but we see other supernovae that go off in other parts of the universe, in our galaxy and other galaxies, and they have very stable statistical properties. So never in physics can I tell you this proton is about to do exactly this, and it did exactly this in the past. That's because of quantum uncertainty. We have no idea there's very sensitive dependence on the current properties upon the past properties. And we just can't have absolute knowledge of it any more than I can say the air molecule right here in the room that I'm breathing into my nostril on my left side right now, I know exactly everything about. No, I don't. But I do know about the collective behavior of all the atoms in this room, which you'd think would be harder, right? It should be harder to get 10 to the 23rd molecules understood than 1. But actually, we understand much more about the aggregate properties. That's what we call temperature, pressure, macroscopic emergent properties of gases when they're in aggregate. So this is a little bit of a long-winded way to say that we have observed the process that formed quarks into protons. That turned quarks into but we haven't observed what created quarks. And it's a good thing you didn't ask me about that, because at 1 second, so remember, we're going backwards in time, so it's a little hard to say, because I don't want to be prejudiced. I don't want to say 1 second after the Big Bang, which is what 99% of my colleagues will do, by the way, and this is a very important distinction. They'll presume that the Big Bang was the creation of time, that time sprang into existence, but we don't know that. And maybe we'll never know that. And I'm not being a flat earth, or creationist or whatever. I'm just saying we know the laws of physics have been immutable since this epoch that was 379,999 years, not 23 hours, 59 minutes, and 59 seconds ago, before the formation of the first hydrogen atom. But we don't know what happened very well. We have never tested on Earth or seen a process like that which created something before that 1 second interval.
Before that moment, there was just quarks, anti-quarks, different types of quarks.
Neutrinos.
And these are things we can't, unlike a proton, unlike an atom, unlike whatever, we can't split a quark. As far as we know, we can't split a quark in half.
Yeah, it's even worse than that. We can't even have a bare quark. In other words, we can have a bare proton. We can have a bare electron. We can even have their antiparticles. We can have an antiproton. We can have an anti-electron. That's called a positron. We can have antineutrinos, but just individual ones. Your eye can detect a single photon, but you can never have a quark by itself. It seems to always come in pairs, as does magnetic magnetic fields. So a magnet, if you take a bar magnet and break it in half, you don't get a north pole and a south pole. You get two north poles and two south poles, north, south, north, south. And quarks seem to be like that. The harder you break them apart, you try to split apart two quarks and a hadron, they rip apart when you supply enough energy. And that amount of energy is just enough to make a quark attached to each one of the quarks that you separated. And so
That's interesting.
Quarks are confined. They're called confinement. But we still understand a tremendous amount about them from these different types. We know how many there are. There's 6 different types of them.
So what's that force that takes the energy and spits off? So when you use enough energy to split a quark in half, what's that energy that splits off a quark?
Well, you're actually supplying that energy. So for you to break apart the quark, you would have to smash together 2 protons together. And then inside the protons, the substructure of the protons, the quarks will come together with enough energy that they'll dissociate from the up. Let's say an up quark was paired with a down quark, et cetera, inside a proton. They'll rip apart. But then you shot in so many photons, or you have put in so much energy that there'll be enough energy in this virtual cloud of energy that in too short a period of time for you to measure, that energy will get converted into matter, and that matter will be another quark to pair up with the other quark.
What's the pairing energy, though? Why does it pair?
Well, it's like because it has to conserve these number of quarks. So the quarks, there seems to be what are called symmetry principles in science. A woman by the name of Emmy Noether, one of the greatest mathematicians of the 20th century, she came up with this rule that when something is conserved, it obeys certain symmetry properties. So when you see a figure skater, she's spinning on her skates. When she pulls her arms in from the outside, she spins up. That's called conservation of angular momentum, and that's related to the fact that she's exhibiting this symmetry under rotations. Like her body's not changing. The inertia of her body is changing as she brings her arms in. It takes energy for her to do that, and so you, the experimentalist, are supplying the energy that then goes into making another quark. So it's kind of like when I talked about creating matter. You can have 2 photons which have no mass. They crash together with enough energy, and out will pop an electron, and out will pop a positron. That's called pair production. So what is conserved there? What has been conserved? What was the initial charge of the photon coming in? What charge electronic charge does a photon have? It's neutral, right? Yeah. So what charge does the outcoming? So you have 2 neutral things coming together. So 0 plus 0 equals 0. The outgoing charge has to be what?
0.
0.
So, because they're smashing into each other, is that like what turns it from energy into mass? Now I know there's this equivalence because of relativity.
Yeah, that's essentially what it is, right? So there are things called virtual particles that can come into and out of existence on timescales shorter than we are capable of measuring them. And yeah, essentially the vacuum, which you think of the vacuum as having 0 charge as well and having 0 mass. So anything that comes into or out of the vacuum has to come in a pair that preserves the amount of charge, something called parity and something called time reversal. But the most common one that we're familiar with is charge. So the vacuum is neutral. There's not like some net electric charge in the vacuum of space. There's a neutrality. And so anything that you create always comes in pairs, and the pairs have to have equal and opposite charge, or they could be neutrinos. Neutrino has the prefix neutral, which means they have 0 charge also. And those things can pop into and out of existence as well without changing the balance of charges. They carry another type of symmetry called lepton number, which is too complicated to get into right now, but that has to be preserved as well. And electrons have certain lepton numbers. So these are all based on what are called symmetry principles, which leads people to make mathematical models of abstract things like triangles. Okay, so an equilateral triangle is perfectly symmetric as triangles go, but not as symmetric as a circle. And so what people will do is they'll look at different ways that these symmetries can manifest themselves in physics, and they'll say there must be some underlying mathematical law. And then you forget about the particles, James. So eventually we'll stop talking about particles and we'll go and just talk about the mathematical properties. So here's a good example. I have this mug here, this mug that Elon Musk gave me from SpaceX. No, I bought it from him. So this thing is not symmetric, right? It has a handle on it. But I can talk about how it behaves under rotation. So if I rotate it, the handle's facing you, I rotate it 180 degrees, the handle's now facing away from you, and I rotate 180 degrees back either way, and now it looks symmetric. So you'd say it's symmetric under rotations. That has a property of a certain mathematical object called a group. So now I can just say, forget about groups, let me put this away. But there are things that don't behave that way. So if I go like this, if I rotate this 10 degrees and then I rotate it 35 degrees, that's the same as rotating at 45 degrees in the beginning, right? That's called commutation. But if I rotate it 90 degrees this way and then 90 degrees this way, that's very different than if I rotated it this way and this way. Like, they don't come back to the same thing. So that's a property of a certain thing called a matrix, which is like an array. And that those matrix multiplications are non-commutative. So in this abstract world, 1 times 2 does not equal 2 times 1. And so, or 2 times 3 or A times B does not equal B times A. And then you stop talking about the stupid particles, and then you just have to talk about the math. And that's what happens. We end up away from the physical properties and move it into purely mathematical domains. So most of what we're talking about are the mathematical properties.
So this is occurring before the protons are made, and now we're trying to figure out what precedes the quarks, essentially?
Yeah, so we don't know what precedes the quarks. We don't know what could have preceded it. One of the best models is this theory of inflation, which could take us back not to half a second, not to 1/36th of a second, but to 10 to the minus 36th of a second. But again, we wouldn't know what happened before that. So now we'd have a decimal place, 35 zeros, and then a 1. And we'd know everything back from 380,000 years ago. Oh, that was a Tuesday. Go all the way back to 1 second, figure out what day that was, go back to 1 apart and 10 to the 36th of a second. What day was that? That was the same day, right? It's on that 1 second. Go all the way back to that very minute fraction of time. But we don't, then the theory is that process called inflation, when it ends, it takes a type of strange substance called a quantum field, a scalar inflaton field, and that field somehow blows up the universe to these tremendous factors of literally 10 to the 30th power, but then it has to end. So it goes from like a size of an atom's proton to the size of a giant beach ball, and that happens over a trillionth of a trillionth of a trillionth of a second. And then where does that energy go after you blow up this balloon? It's kind of like hot, but inside it might have cooled off because you expanded so much. Somehow the universe has to have that energy restored to then produce the heat that kept the protons from binding to the electrons for 380,000 years. So that process is called inflation. Now, again, I once said time had to have a beginning.
This is such a valuable service for all business owners, big businesses, small businesses, doesn't matter. I wish I had this in the many different businesses that I've started. Sometimes it seems like your business is humming, but then suddenly you don't understand it. You're starting to fall behind. You're not understanding where your costs are, where your revenues are, where your payments are. Teams are buried in all sorts of like BS work, and you can't seem to close the books. So you need like one dashboard, one source of truth. I'm jealous of this business, NetSuite from Oracle, of course, NetSuite by Oracle. I wish I'd come up with this idea. It's a brilliant concept to have all your business intelligence on one dashboard. This is why you need to know these 3 numbers: 37,000, 25, and 1. So 37,000, that's the number of businesses which have upgraded to NetSuite by Oracle. NetSuite is the #1 cloud financial system, streamlining accounting, financial management, inventory, HR, and more. 25. NetSuite turns 25 this year. That's 25 years of helping businesses do more with less, close their books in days, not weeks, and drive down costs. 1, because your business is one of a kind. So you get a customized solution for all of your key performance indicators, your KPIs, in one efficient system with one source of truth. Manage risk, get reliable forecasts, and improve margins. Everything you need to grow, all in one place. So right now, download NetSuite's popular KPI checklist designed to give you consistently excellent performance, absolutely free, at netsuite.com/James. That's netsuite.com/James to get your own KPI checklist. netsuite.com/James. You know what I love about fantasy sports is that even though I'm not going to be a great basketball player or a baseball player or a football player or whatever, I feel like I get to participate and make decisions and use my knowledge of these different leagues or these different sports to compete. So it's like I can pick my team or I can pick my favorite players and I could use my knowledge to make predictions and maybe even make money. So with the basketball season here, you can now pick combo projections across football and basketball from the Specials League on Prize Picks. This is a league created specifically for combo projections that include two or more players from different sports or leagues. Want to play alongside some of Prize Picks' favorite players like rapper Meek Mill and comedian Andrew Schultz, who's also been a guest on this podcast, and I've been a guest on his? You can now find community plays under the promos tab of the app to view entries for some of the biggest names in the Prize Picks community each week. Look, Prize Picks even offers a reboot policy so that your entries stay in play even if one of your players gets injured. For football and basketball games, if you have a player who exits the game in the first half and does not return in the second, that player is rebooted. Prize Picks is the only daily fantasy sports platform with an injury insurance policy. What? So I love playing it. I love anywhere where I can use analytical ability with my interests to demonstrate some skill and maybe make some money. And I like the game-like aspect. I do wish they had chess as a category on prizepicks.com, but I'll settle for what they've got. Maybe I should make my own fantasy chess league. But in any case, I love Prize Picks. Go to prizepicks.com/James. Use code James for a first deposit match up to $100. That's the easiest $100 you're ever going to make. So that's prizepicks.com/James and use code James. Daily fantasy sports made easy. The future of learning is definitely online. Like, it's such BS that you have to spend $200,000 or take $200,000 in loans and go to some fancy school when it's useless. It doesn't guarantee you a job. Most employers, including me, do not care about degrees or grades or anything like that. We want to care that you love what you're doing, that you know what you're doing, in some cases that you have experience or that you're willing to learn. But people in general love learning and are curious. Like, the key to success is curiosity. And I think masterclass.com is the perfect model for online learning. I'm really happy they're sponsoring this episode. If you're going to give a gift, give the gift of learning. Masterclass makes a meaningful gift this season for you and anyone on your list, because both of you can learn from the best to become your best, from leadership to effective communication to cooking. Let me tell you some of the classes I've taken. I've taken comedy from Steve Martin. I mean, can you believe I can take a class from Steve Martin on comedy, or Judd Apatow, my favorite comedy director? I could take an actual class from him on writing. Wolfgang Puck on cooking. Dan Brown on writing, or Judy Bloom, who's been on this podcast, on writing. By the way, Wolfgang Puck also has been on this podcast. It's such a pleasure. I try to take classes all the time from masterclass.com. And whether you're watching Masterclass on TV or listening in audio mode in the app or on their site, the quality speaks for itself. It's like these Masterclass instructors are your own personal mentors that are going to help you reach the next level. How much would it cost to take one-on-one classes on comedy from Steve Martin or on chess from Gary Kasparov? You just wouldn't be able to do it. But it would cost hundreds of thousands of dollars. With a Masterclass annual membership, it's $10 a month. Memberships start at $120 a year for unlimited access to one-on-one classes with all 180 plus Masterclass instructors. So it's not just $120 for one instructor. You get all 180 plus Masterclass instructors. Boost your confidence and find practical takeaways you can apply to your life and at work. And if you own a business or are a team leader, use Masterclass to empower and create future-ready employees and leaders. That's the real education in today's world. So this holiday season, you can give one annual membership and get one free at masterclass.com/JAS. JAS, of course, stands for the James Altucher Show. So right now you can get two memberships for the price of one at masterclass.com/JAS. Masterclass.com/JAS. Offer terms apply. So could it be the case, because now we're beyond our normal understanding of physics, that means we're beyond our normal understanding of time. Could it be the case that it works like, a derivative in calculus, so that we're just always getting infinitely closer to the beginning of time, but time has slowed in some way,
Yeah.
so that we never quite get there?
The question is slowed with respect to what? And this happens a lot in science where people give me kind of reasons. They say, oh, well, the Bible is actually, they know I'm Jewishly practitioner of Judaism. And they'll say, oh, well, here's the first 7 days of creation. Here's my model. There's actually a very well-known scientist who went to MIT and is a rabbi in Israel. And he has this huge following and books called the Genesis and the Big Bang. And he shows you how it works, that the actual 7 days of creation actually took, when he wrote the book, it was like 15 billion years in 1990. So, it's off by a billion years, 2 billion years. Oh, well, what's that between friends? Well, actually, it's kind of off way more than that, because he's talking about the evolution of time from some supernatural perspective. So there's something in relativity called the twin paradox. Have you ever heard of that?
No.
So the twin paradox, I think it's manifest in some of these movies like Contact with, remember Ellie Arroway goes off and she goes into the spaceship, and this is Carl Sagan's book. She goes off into this wormhole basically and comes back, but everybody on Earth is aged a lot. This takes place in Interstellar, the same kinds of things, right? What you're looking at is that time is relative. And that's the first thing that we really have to apprehend. There's no notion of something that's simultaneous to two people. So Einstein thought about this. He was like, if you're on a train and you're moving towards a lightning bolt that hits the track far ahead of you, you'll see that at a different moment than someone who's stationary with respect to the train. And that notion is what led him to really contemplate that time is not constant for all observers. Time depends on the relative velocity, and the simultaneity observed depends on your velocity relative to one another. And so two people will not measure the same length of time, and two people will not agree in general on the length of an object. So a famous example is called the ladder paradox. You can have a ladder that's 11 feet long, and it can have a barn that has a width between its front and its back door of 10 feet. And if you're going fast enough, that ladder will fit inside the barn for some brief amount of time. But to somebody else on the ground, it will always have the same length of 11 feet. So how is that possible? That's called length contraction. So intervals get longer and distances shrink. It's called Fitzgerald contraction. The length physically, the chemical forces that transmit the molecular strength of an object can get deformed when something is moving at high velocities relative to a stationary observer. But of course, we're all in motion with respect to, nobody can say I am the center of the universe. We know that. And so it's not possible to say that there is one absolute standard of reference. That was Einstein's realization that led to the constancy of the speed of light as the ultimate cosmic speed limit. And he also used these laws to derive different properties of things in motion. And so it's not really possible to say exactly when something was created that every single person in the universe would agree upon being accurate.
But at this point where we don't really understand what energy is, and we don't really understand what mass is, but we know that inflation could go faster than the speed of light because it's not energy or mass, right? So it could be the concept of time is just completely different at this point.
Yeah, you can ask the question, what would the rate of events that occur on Earth be? So, for example, there are particles called muons. These are subatomic particles. They're like heavy versions of the electron. The electron binge ate too much and it got too heavy. But unlike the electron, these things die. So we don't think the electrons have a lifetime. They live forever. We think the protons probably live forever. But muons don't. They only live for about a few hundred microseconds, and then they die. So you make one in your lab. I can actually make one. I can actually watch it. It's actually half a millisecond. It's not that short a period of time. It's not like trillionth of a second. And you can measure it. It will decay until I believe it'll decay until, some particles of light, actually a photon that I can detect with a light detector. And I don't know if I ever got around to this earlier in the conversation, but I was talking about single particles. So your eye can detect a single photon. And actually, your eye can't detect this particular muon decay photon, but I can make a sodium iodide detector, and it will detect it. That muon lasts for 500 microseconds, call it, on Earth, in my lab. But when they come from space, they're moving near the speed of light, and they'll actually live longer. And we know that they live longer than they do at rest because they would decay. It takes longer than 500 microseconds to go from the top of the atmosphere when they get created to the laboratory where we detect them on Earth. So by moving at high velocities, they extend their lifetime relative to what they would if their cousin or their twin on Earth would do. So there is a relativity of time, and that does depend on motion. It also depends on gravity. The fact that the early universe was known to be much denser, had higher average gravitational force, and processes were taking place at very high rates of speed compared to today. Yes, it is possible that time as a whole, but the question is, the universe didn't know that it was like really, really dense. I mean, at a certain point, gravity is irrelevant after this epoch at which inflation reportedly would have taken place. So then you can just apply the laws of chemistry, et cetera, now. So there's nothing that stops us. Like we're actually moving right now through the galaxy at hundreds of kilometers per second, faster than bullets and anything that you've ever seen, any spaceship we could ever make. We orbit around the entire galaxy once every 200 million years, and the galaxy is hundreds of thousands of light years across. So we don't know that we're not actually moving at tremendous speeds through the multiverse or through the universe itself. I mean, there's nothing to measure it except for other galaxies. But if we're all moving relative to something at tremendously high rates, it doesn't affect how we observe or perceive time ourselves. So even in the early universe, it could have been this hotbed of activity, of expansion of gravitation, but you have to ask relative to what are you asking how did this process take place? So if I have my lab and I have a muon at the trillionth of a second after the Big Bang, or let's call it 1 second after the Big Bang when muon physics could start, we would measure the same lifetime relative to our lab. I mean, our lab would be destroyed, but the point is the physics hasn't changed in terms of clocks that are at rest with respect to the object under study.
So what's the theories then about, there's either no theory, like there's this singularity that we still don't quite understand completely the beginning. There's this infinitely, like you said, zero energy, zero mass thing that heats up and explodes and then inflation starts. Or there's like this big bounce that everything got crunched down. The universe has been around forever, and we've been constantly expanding out and then contracting back in to some huge dense point that gets heated up to the point where it then explodes out without really disturbing the laws of physics, because it doesn't get infinitely small.
It could, right? So that's called a classical bounce. So remember, there's one very overarching problem that plagues physics. In addition to this problem of how the universe gets started, our second book will be about theories of everything. What does it mean to be a theory of everything? It means that there's four forces of nature. There's electricity and magnetism, which are actually one force. Thanks to James Clerk Maxwell, we understand that to be the case. In other words, 1600s, Galileo was working with a magnet, and he thought that was totally different than when he would rub, his cat's hair and get a shock when he touched something metallic. He thought they were two different things. They're actually interrelated phenomenon that are two sides of the same coin that we call now electromagnetism. In the 1950s and 60s, they realized that actually those two forces that were once disparate and disunified actually unify with one of the other forces that is thought to pervade through the nucleus, called the weak nuclear force. This is the one that's responsible for radioactive decay, beta decay, other types of neutrino physics. Those are called weakly interacting physics. Those forces and electricity and magnetism are all one force. We now call that electroweak. And then there's another force called the strong force, which is a nuclear force that allows the two protons in a helium nucleus to bind together, even though they have got this massive amount of electrical repulsive force that should crack them apart. There's a stronger force, stronger than the force of electricity that's repelling them. The stronger force, called the strong force, sucks them together with a force greater than that of the electrical repulsion. And that's called the strong force. So now we've got three forces: strong force, weak force in the nucleus, and then the electromagnetic force. So those three forces can be thought of as very distinct from gravity. in that we understand how they behave at the quantum level. The two nuclear forces, the only way to think about them is in terms of quantum mechanics. You never see aspects of the nuclear force on everyday life. There's no like quark nearby to cause you to, change how you're walking down the sidewalk, tilt one way or another. But there is obviously manifestation of electricity in your daily life. That's how, you get your hair to look so nice. And and also there's obviously gravity is what
That's definitely electromagnetism.
that's the effect you had on Robin. But the gravitational force is the most familiar to us, but it's also the weakest force of all, except perhaps when the universe was tremendously smaller than it is today, namely after the beginning of time, if there was a beginning, after the previous crunch that collapsed the previous universe to be what it looks like today. And so there's two different ways the universe can crunch, and this is what I'm getting to now, or collapse. It could collapse to a singularity, but that has all these attendant problems. How do you go from finite universe that pre-existed our universe today? How do you collapse it to a point with zero spatial extent over an infinitesimal point in time? And then how do you transit? So how do you go from something finite to something infinitesimal? We just don't know. And then how do you go from that infinitesimal back to a classical macroscopic enlarged object like our current universe? So that's a problem.
And so it seems like literally this point right here is the crux of all the theories of all the different theories of how the universe could have began.
Yeah, so that is certainly one of the biggest problems. It may not be required to under the model of folks like Sir Roger Penrose and Paul Steinhardt. They are now working on totally what are called classical, which is in contradistinction to quantum. So there's classical mechanics discovered by Galileo, Isaac Newton, where you drop bowling balls and feathers and whatnot, and even go to the moon via a rocket ship. That doesn't require any quantum mechanics. And then there's quantum mechanics, which requires that you have a totally different type. You go from Newton's equation, which is F equals ma, force equals the mass of the object times the acceleration. That's how much force you need to apply to a 1 kilogram mass to get it to accelerate at 9.8 meters per second squared, what have you. And the product of those two, mass times acceleration, what we call weight. So that's a dominant law of classical mechanics. The dominant law of quantum mechanics is called the Schrödinger equation. And that gives some kind of relationship between the energy of a system and what we call its wave function, which is totally different than the Newtonian description of position, acceleration, and velocity. So there is a quantum realm beneath which you must only use quantum mechanics and above which you can use classical mechanics. In their laws, in Penrose's and in Steinhardt and company, they don't require a singularity. Their model goes never through a singularity, and therefore they don't require quantum gravity. And that's a huge advantage to their model. But there are predictions that it makes which allow us to prove it wrong, but there are no predictions that we can think about that we could prove it right. And so that's the problem with cosmology.
So I wanna understand this a little more. So
Yeah.
As things get smaller and smaller, classical mechanics go away. Now we're in the quantum world. So instead of an object having a location, which you could measure the time it's at a certain spot, now everything's a wave, and measurement gets all hairy. Like, how do you measure a wave?
Mm-hmm.
And that's where sort of observation changes the result, is how you observe it.
Right.
And why does that though remain? Why does it solve the problem of a singularity? Why do you never need a singularity then?
Well, I wouldn't say that it's just the fact that you. It's the fact that you never get down to the quantum scale. Like, what if I said the universe collapses, but it collapses to the size of our galaxy? Like the previous existing universe collapses the size of our galaxy. There's nothing about quantum mechanics that operates on the scale of our galaxy. So it would be unnecessary. Theoretically, you could apply the laws of quantum mechanics to macroscopic systems. You could actually predict the flight of a baseball using quantum mechanics. I mean, theoretically, no one's ever been able to do that. In other words, treat each of the 10 to the 28th particles inside of a baseball, treat that as a quantum system behaving in certain ways, apply the Schrödinger equation, and there are ways to get, people have done it, but it's a very difficult thing to do, and it's unnecessary. It's like it's using a howitzer to kill a mosquito. And so in this case, we would not need the apparatus that people that are trying to develop quantum gravitational theories, such as string theory, such as M theory, such as geometric unity, or my friend Eric Weinstein, we would never get to a quantum scale where quantum gravity is even relevant. So in other words, we're supposing it exists. But part of this thing I did with PBS on YouTube a couple of weeks ago is really dedicated in part to the question of why do we think we need a theory of everything? So when I say theory of everything, that means making a quantum mechanical version of gravity. Does that make sense? So the gravity version is what makes the TOE. It puts the everything in the theory of everything, without which we don't need that. We have quantum theory of the two nuclear forces and the electric force and the magnetic force and the weak force. We're good there. So now you get a letter from God and it says, actually, the universe never collapsed to this quantum state. Well, we don't need a theory of quantum gravity then. Maybe you do inside of a black hole, but you don't to answer the question that you and I are talking about, which is, did the universe have a singular origin, or is there some other form in which the universe could have emerged? So if you knew that, there'd be a whole, like, people would just quit working on string theory. Well, maybe they wouldn't. I don't know. Like, if you just knew the universe was never quantum mechanical, gravity was not relevant for quantum mechanics, at least in cosmological scenarios. Again, you might care about it when it comes to black hole singularities, but we wouldn't need it. It would be unnecessary.
So in this view of the beginning of the universe, this is the expansion, contraction, over and over again. And the universe has been around forever. We've had infinite number of universes in the past, infinite number of universes in the future. Possibly. I understand there's different theories about that as well, but that's the basic idea, is that at some point things crunch down so much that it gets too hot and it explodes again.
If the universe undergoes this tremendous collapse, but again, we still haven't answered the question of, was there a beginning, right? So there could be one universe, although it seems unlikely. So in that model, what's required at least is that there's one universe that preceded our universe. It could be that there were two. It could be that there's an infinite number of universes, right?
If there's more than one, doesn't there have to be infinite?
Not necessarily. I guess the question is, you would not be able to, does the universe collapsing, does that erase traces of any universe that existed before it collapsed? In other words, is there quantum erasing taking place where the collapse is so thorough, so efficient, it rearranges any piece of evidence, any shred of evidence that could have residually pervaded following this collapse function? And in my mind, yes, it has to do that, because otherwise it's incredibly it's essentially impossible to figure out how do we start the universe off at this tremendously precise set of conditions that then allow it to inflate. It does have a form of inflation, even though it's an enemy model of, and actually Paul Steinhardt, who's one of the fathers of it, and also the father of inflation, one of the fathers of the modern version of inflation, that is really totally distinct from, in most ways, except for the fact it has certain properties like a scalar field, quantum mechanical energy.
Well, there still could be inflation, right? It still could collapse really, really small, and the explosion still could have that inflationary aspect, which is why the universe is still expanding faster than the speed of light.
At that time, at the early time, right? So actually, it doesn't require in their model a faster than light expansion. It does away with the main problems. Again, so the Big Bang model was really successful compared to its alternative, which was the steady state model. Then the steady state said, oh, well, we're going to tweak our model and put in, that was version, alpha version. Now we got the beta version. That's called the quasi-steady state. And that had some properties that are very similar to what we call dark energy and the scalar field, this creation field that we talked about last time, where all that was required was one atom of hydrogen every century in a volume the size of the Empire State Building. So very plausible that such a thing could happen. When you think about how much matter, how many Empire State Buildings can fit in the observable universe, though, you realize extremely high amounts of matter and energy associated to do that. But nevertheless, it had properties that kind of anticipated, presaging what we think about now as dark energy in the accelerating universe. Those were thought about by people in the 1950s. And again, so then what comes along now is inflation to solve some of the problems in the Big Bang Theory. Namely, why does the universe have the particular features that it does? In particular, features that are believed to be prerequisites for life. and for us to ask the question of why is there a universe? So in the case of inflation, now there's alternatives to inflation. So for a long time, there was only the Big Bang. Then there came the quasi-steady state. Well, first of all, there was the steady state eternal universe. That was the most successful by longevity, right? That lasted for 2,000 years.
And then there was the contradictions, though, which you discussed last episode of this.
That's right. And also in the book, Losing the Nobel Prize, I talk about how that we've cycled through these different things, and we're likely to keep on doing it. The fact that we think we're going to come up with the final answer today, not today, but in modern physics in our lifetimes is a lot of like wishful thinking in some ways. It shouldn't dissuade us from trying to do so, but it's kind of a little bit hubristic to think we're going to live in the era when we can find this out. I'm hoping that we do, but I'm not expecting that we do. But anyway, yeah, so inflation then solved some of the problems in the Big Bang model that was anti-fragile, right? So the steady state helped the Big Bang remove some of its fallacies and some of the problems with it, like the universe being younger than the stars within it, et cetera. And it pointed out those things, made it more resilient, more anti-fragile, like New York City, according to some comedians, very full of grit and resilience. But nevertheless, as we then the Big Bang emerged victorious, it still had these contenders, wondering why does it have these peculiar features? Why does it look the same in every direction we look, even though these regions of the universe are so far apart, unless we bolt on some extra apparatus? And that was part of the original motivation for inflation, to make the universe able to reconcile the fact that it looks the same no matter if you look 40 billion light years to the east or 40 billion light years to the west, it looks identical. And that's a mystery in the classical Big Bang model without inflation. So then inflation came along, solved that mystery, but then it raises other mysteries. How did inflation start? How does inflation end? What is the impact of having a multiverse on, how we think about the predictability of future events? And it still doesn't answer the question of, as I said, how does it begin? It's kind of like, you're not responsible for describing how you began, but, you're responsible for describing how you better have a good story for how your kids began, right?
Right.
So
wait, there's the big bounce, though, the idea that it expands and contracts. This solves the problem of how it begins. Like, it contracts until it's hot enough to explode again. Does it explain why, or if you combine that with some kind of inflation, that does explain why it looks the same in every direction, right?
Yeah.
So why isn't this just the accepted theory? It's the Occam's razor of origin theories.
Well, because it makes predictions that come along concomitantly with the bounce, that are directly in opposition to the inflation model. So it predicts the absence of what are called gravitational waves, which are the very feature that we designed the BICEP 2 telescope to detect. Remember, so inflation, you should think about as somehow predicting that there are waves of gravity pervading the entire universe, in particular originating at 10 to the minus 36th of a second. These waves of gravity persist. They have infinite lifetimes like a photon, and therefore they can live to be 380,000 years old. Then they can shake up the universe's plasma that form the CMB light, and we can detect the pattern of the shaking up via its polarization. The bouncing models lack that completely. There is no inflationary expansion. There is no quantum mechanical fluctuations that lead to what are called gravitational waves in the early universe. So in that sense, they make radically different and testable predictions. So how would you test?
Wait, why do they preclude gravitational waves? Because it was gravitational waves that caused the contraction.
No,
right?
No. It was gravity that caused the. So gravity can be thought about. You think about gravity as a bowling ball and a trampoline. The more massive the bowling ball, the more the trampoline gets deflected downward, and the more sharply curved an orbit would be of a pebble orbiting around the bowling ball. But gravitational waves are like, now you jiggle the bowling ball. In addition to its mass, you move it up and down by 1 millimeter every second. You'd make ripples in the surface in addition to the overall depth, curvature, depression of the trampoline. You can also add another type of curvature that's much higher frequency. Those are waves of gravity. But they don't have anything to do with the collapse of the universe previous to it. So in other words, the collapse of the universe is not the same, and even the expansion of the universe due to inflation is not the source of gravitational waves that we would possibly detect using the BICEP2 or Simon's Observatory. They're extra things that we add on when you have a new substance that has never been seen before called the inflaton. So inflation says what caused it to expand is a substance called the inflaton. And it's very similar to the dark energy that causes the universe to expand today or accelerate today. So not only are galaxies flying apart at a certain rate today, that rate of change will be bigger tomorrow. So the Andromeda galaxy is being pulled close to us, but forget about that. Imagine the Whirlpool galaxy is moving away from us at some fraction of the speed of light, a few percent of the speed of light. Tomorrow, it'll be 1% big, of the speed of light. In other words, the rate of change of that velocity is positive. That's called acceleration. We call that a force that's driving that dark energy, but there's no gravitational waves associated with the expansion of the universe.
Now, this is where also, not only will I ask a naive question,
No, it's
but
fine.
this is where also I feel like the theories of the origin start to play with science fiction, meaning they become guesses with less and less observational ability and theoretical understanding.
Yeah.
So for instance, dark energy, like we could be constantly expanding inside some other universe with a different set of properties, and dark energy could be the gravitational pull of that outside universe. And that's one example of a multiverse theory where we're a universe inside a universe inside a universe forever.
Well, there are technical reasons that can't be true, but I get your point that there could be an external observers, something outside the universe that affects the universe. We actually have very strict limits on that, but I do agree with what you just said. There's more and more science fiction, the more and more speculation has to be applied, and that means the farther we get out from laboratory tabletop physics. The laboratory can allow us to test things at 1 second, 1 second mark after the collapse reached its minimum, or the universe emerged from a singularity, or the universe emerged from a classical bounce. So we could talk about like that, but you're right, because we can't test that physics with anything on Earth. So what constitutes scientific proof to you? Like you were saying before, we've never seen it, but again, we accept things, that if we drop something down tomorrow, it'll still fall to the ground.
Right, but I've read that they theorize 97% of the universe is dark energy, and yet we have no understanding of any of the properties of dark energy, which suggests to me it's somehow outside the laws of what we think of as physics for our universe, which suggests maybe there's something else with slightly different laws or different properties.
I'm not as pessimistic. I mean, I'm usually fairly contrarian, but I'm not as pessimistic as you in the sense that, look, go back to 1859, journey with me, and you'll realize that there was a set of physicists that thought you could never have a wave in a vacuum. You could never have a wave outside of, an ocean, a liquid, a gas, or even solids have waves in them. And now we know that waves can go right through nothing, through the vacuum. And that's very strange. Something that you might have said, Newton actually thought that gravity traveled faster than the speed of light. In other words, if the sun disappeared right now, we wouldn't see it for 8 minutes. I mean, he knew that it took some amount of time. They were starting to realize that light traveled at a finite speed by that time, but he didn't know how much it was. But his laws of gravity have no time in it. Therefore, it would happen instantaneously. We'd go off the rails and lose orbit around the sun, and it would disappear instantaneously. So we'd see the sun getting smaller or whatever, but it would eventually get extinguished. But we already would have this terrible, gravitational catastrophe taking place instantaneously. So he thought gravity traveled faster than the speed of light, and that was totally wrong. But how else was he supposed to reconcile that with observations? Because they didn't know how you could time the speed of gravity. And in fact, we've only realized that gravity, we've only proven that gravity travels at the speed of light very, very recently, when we've been able to detect waves of gravity traveling across the universe at great distances.
And again, this was BICEP2, the telescope that you worked on.
Well, this is LIGO. This is actually the LIGO experiment detected gravitational waves directly for the first time in 2015, that they then later were able to see an explosion of a star take place, and they saw the flash of light associated with the star exploding, and then simultaneously they could detect the waves of gravity from that, almost simultaneously within the experimental uncertainties. And so that proved that gravity travels at the speed of light. Otherwise, it's very hard to do in a direct experiment. I mean, we could do things that would suggest, gravitational force travels at the speed of light, but it's very hard to arrange a gravitational experiment right? Because you need so much, all the matter of the Earth. If you put a certain number of of electrons on a piece of matter the size of a paperclip, that paperclip will be attracted to another paperclip. You've probably done that. You get some. It's only like a couple million charges or whatever of the electronic charge that will cause a paperclip. You can actually get it to levitate, or a magnet. You've had a magnet, put it on another magnet, it can levitate. That's resisting the mass of the entire Earth, of every single particle that makes up gravitational force, is being resisted by this tiny little magnet that you can hold on your pinky. And that shows you how weak gravity is. So it's very hard to do an experiment where an experiment, you want to accentuate the effect that you're trying to study. In this case, gravity is very hard to experiment with. But we now know that gravity does travel essentially at the speed of light. And so we were trying to do that with the Bicep 2, but of course we were, premature in the announcement. And part of that is because of how difficult it is to do what we're doing. Not only is it hard to do it just based on the weakness and the paucity of strength of the forces that we're trying to measure and the distances these things have been traveling over and through, but we're also looking through the Earth's atmosphere, we're looking through the galaxy, we're looking through other galaxies. It's extremely fraught, perilous, and difficult to do for those reasons. So I agree with you. I mean, just circling back, it is kind of like science fiction. That's what Arthur C. Clarke said. He said, any sufficiently advanced technology is indistinguishable from magic. And here's this great science fiction writer. And he's really reveling in this fact that it is almost incomprehensible that we actually understand things like this. What happens in a supernova? What makes the sun shine? They didn't know that 120 years ago.
So your theory is then dark energy, we haven't been able to observe it yet, but maybe in 100 years we'll have some better equipment to observe and more theoretical understanding of what it might be, and that it's not necessarily something in the other.
Yeah, exactly. Just as the ether that we did away with only in the last century, so too will we. Maybe we'll do away with dark energy, or maybe we'll understand it even better. But it's bad to be hopeless and depressed about it because, and I think you look back in the history of understanding, we're the first generation that can really understand how, on rough scales, that we came to be, that the matter in our bodies came to be, that evolution took place, that some event formed the earliest material in the universe. We don't know what that event is, but we know that the material formed by the laws of physics that we understand today. So I'm sanguine. We'll understand more and more. Whether it's 100 years, I don't know. I'll keep taking my vitamins.
So wait, so what do you believe in? Like, do you believe in some sort of big bounce, like a contractions, expansion, contraction, expansion?
Yeah. So again, we agreed that we wouldn't talk about what we believe. We talk about what we have evidence for. So actually, we have evidence for neither one. I mean, we have evidence for what's happened after a certain early period. We'll just call it the 1 second mark. So we'll just start everything at 1 second. So after 1 second, I have a tremendous amount of knowledge, thanks to my colleagues and all the giants whose shoulders I stand on. We understand it exquisitely well. But that massive gap between 1 second and whatever came before it is truly daunting. And so I don't have any evidence for it. So therefore, I don't believe in it. Like, I don't have to believe in inflation and evolution. We have evidence for it. Could prove that evolution. I can take 1,000 generations of bacteria, change them a little bit, they'll evolve. How did speciation occur? How did origin of life occur? We don't have evidence for that yet.
Right. But then that's where, there's this Occam's razor principle, which is like the simplest explanation is probably the most correct. So it seems to me, with my limited understanding, the simplest explanation is we don't break the law, and, things contract to a point that we can understand conceptually. It gets so hot that it has to explode again. And, things expand for trillions of years and then they start to contract again, and until they're really small and hot and so on.
Well, what's interesting to me is that you could falsify more than the bounce model. Again, you can't prove inflation took place. So imagine tomorrow I say inflation took place. Remember I said this last time. The same day we said that, some group of atheists, Lawrence Krauss and others, said this proves there's no supernatural being. And then the Discovery Institute, which is like the anti-Krauss, they said this proves that God exists. So it's like, if inflation took place, you can't go as far in a certain sense. And so for that reason, because it has to be essentially a multiverse, there has to be an infinite spectrum of universes that exist, that are dead, that don't exist anymore, some that have properties very different, somewhere you're in San Diego, I'm in Florida, whatever. Somewhere Jerry Seinfeld's in Nashville, Tennessee. But that
might be impossible.
Yeah, that's a forbidden fruit there. But in any case, how can we possibly know what happened if there is a multiverse? So that's a huge objection to inflation. In other words, if inflation, then multiverse. That's the syllogism you have to think. Syllogism, another word that sounds dirty, but it's not dirty.
So it's a multiverse has to exist because you're basically defining a universe as beginning with the explosion and
how did the inflaton get there?
With the contraction.
Right. How did the inflationary energy get there? It had to be borrowed from the vacuum. It had to be something that pre-existed inflation. And it's almost impossible to shut off the expansion in every region of the universe. Therefore, there'll be bubbling universes that percolate into existence throughout eternally for all time.
Which also is a theory, right?
That is.
We're dropping off singularities all over the place, which are then exploding into their own universes.
Yeah, exactly. That's the eternal inflation model. People like Lindick.
Well, and there's also the idea, or maybe this is the same one, but that there were multiple singularities all around.
Yeah.
So infinitely far away, or almost infinitely far away, if you could say that, there's other singularities that burst at different points and pushed us away, and we pushed them away,
Right.
and we never see them. Perhaps this could be the dark energy, as some inter-universal force.
It turns out that gravity, it doesn't work that way. Gravity, so in other words, if you're on the surface of the Earth, let's say we live on the surface of the Earth, we feel some weight. You've come out of quarantine, thug quarantine, with a 6-pack. I have not. I've come out with a 2-liter bottle. But let's say there's another shell added to the Earth's surface, above the Earth's surface at 6 foot 1 inches above, the Earth's surface. So we're comfortable. But there's a mass that's like a black hole, just a tremendous amount of mass surrounding us, outside of us. We wouldn't feel any heavier. So the external influence of all the matter external to us doesn't affect how much we weigh. It's the matter internal to the center of the Earth. Does that make sense?
Right, but that's why I'm saying. And again, maybe I'm over trying to understand dark energy, but that's why I'm saying there's some other energy in this exoverse outside of us that interacts between universes.
It would have to be homogeneously distributed like that shell, and therefore it would have no net vector to cause us to expand towards it. In other words, if you have all these like points of mass or some other universes outside that are causing us to gravitationally accelerate, we are only being afflicted by the mass that's internal to, if you will, our universe by itself.
Right, so we can't observe what's out there.
Some say
but it
you
might
could.
be out there.
Some say that our universe could overtake another universe. In other words, a universe here is expanding slower because it has less dark energy than our universe. It's otherwise identical. I mean, you live in Florida and I live in Blafalornia, but it's identical. Every other thing, but it's expanding slightly less quickly than ours, and then our universe kind of overtakes it, and our bubbles of universe merge together. We would be able to detect that according to some very well-respected theoretical calculations. But the odds of that happening are incredibly low because the average distance between us and the nearest universe in the multiverse, in a parallel universe scheme of the multiverse, is like 10 to the 10 to the 116. So it's a number 10 raised to the power, the number 10 with 116 zero. Like you couldn't write it down if you wrote down 1 0 every second for like the rest of your life. Like you could never even write that number down, let alone think that you're going to come into contact with a universe that many miles away from us, if you will.
So
James, can we take like a 15, 20-minute break, pick it up another time, or?
Yeah, do you want to do a part 3? Because I feel like we haven't gotten into any of the string theories or the simulation theory.
Yeah, I know. Those are the really fun things.
Yeah, no, that's great. Because I also have a list of theories. We haven't gotten into the brain universes. We haven't gotten into different dimensions colliding, creating the inflatons, I guess, and the simulation theory and gravity's rainbow and so on.
Entresto, sacubitril valsartan tablets, is the #1 heart failure brand prescribed by cardiologists and has helped over 1 million people with heart failure. It's a prescription medicine that treats adults with long-lasting chronic heart failure and works better when the heart cannot pump a normal amount of blood to the body.
Don't take Entresto if pregnant. It can cause harm or death to an unborn baby. Don't take Entresto with an ACE inhibitor or aliskiren, or if you've had angioedema with an ACE or ARB. Don't take with aliskiren or within 36 hours of taking an ACE inhibitor. The most serious side effects are angioedema, low blood pressure, kidney problems, or high blood potassium. Angioedema is swelling of your face, lips, tongue, and throat that may cause death. If it causes difficulty breathing, get emergency help.
Ask your doctor about Entresto. To learn more, visit support.entresto.com or call 833-446-6699. For pricing, visit Entresto.com/cost. If you can't afford your medication, Novartis may be able to help.